I have yet to see a PhD in a philosophy department contribute materially to our understanding of the physical sciences.
Saying that something is only important in as much as it contributes to science is a really dangerous point of view. When Einstein wrote an obituary that everybody read for Mach, he said, one of the reasons I hold this person in such high esteem as a physicist is because he kept asking about what is the proper goal of science. And that guided how he did science. And when we have conversation, it's interesting because I change the way I think about how physics is being done right now. I learn about what they consider the interesting questions. It is worth doing in its own right.
This is StarTalk. Neil deGrasse Tyson, you're a personal astrophysicist. Got with me Chuck Knight, baby.
Hey.
Lord of Comedy.
That that sounds so.
It does sound
like pretentious.
But people call you Lord Nice, and
yes.
So why not run its course?
Because it sounds like I should say I am the Lord of Comedy. Like when people are like Lord Nice, that sounds kind of cool. Like, you know what I mean? It sounds like a term of endearment, more so than a title. The way they say it.
I got you.
But when I say it, it's just like, bow down before me.
Bend the knee.
Exactly. Will you bend the knee before the Lord of Comedy? Laugh not, I say, but capitulate.
We're revisiting the philosophy of physics.
All right. Couldn't get enough the first time.
It triggered a lot of interest.
Okay.
More than I expected or anticipated. And so...
A lot of people like philosophy.
I think so.
Did you bullshit today?
Is that what that...
Are you planning on bullshitting?
Well, we have an authentic philosopher in the house once again, Elise Crull. Elise,
hey,
welcome back to StarTalk.
Hey, everybody.
Have you bullshitted today yet?
Yes, but not about philosophy.
All right. Good answer.
So let's remind people.
Good answer.
So you're an associate professor of philosophy at CUNY, City University of New York, City College. My father was an administrator there many moons ago. And your background is entirely in physics and philosophy. And I think there's some math in there too. Is that right? Or was there?
There's some history.
Oh, history.
I was one class away from getting a minor in math, and I decided to take tap dance instead. And no looking back, man.
No,
tap dance is
right.
Great.
Yo, you got to move that body. Move that body. And so I love this. And you have a specialty in the history of quantum physics. Is that
the history and philosophy of
quantum physics?
Yeah,
because there's a lot of room to philosophize there. Let me tell you.
Yes.
Because I'm happy to just calculate, but somebody's thinking about why. And I'm glad that's not me. Somebody else is doing that. And so part of why we have you back on, I'm reminded by not only my producers, but the comment thread that I might have been, or was certainly over exuberant in my conversation with you. Way beyond what is normal. Maybe I had a lot of thoughts and feelings, but you're the guest.
That's hard to believe.
No. Hard to believe that
Look, I'm going to choose to understand it as, you guys have a great rapport. And what I do is intrinsically interesting. So it gets people...
We were all in it.
We're in it.
Yes. I was totally in it, but I want to make sure, because I'm an educator first.
Yeah.
And I want to make sure that people come into this conversation more thoroughly informed, and so that they can become enlightened.
I appreciate that, Neil.
Yeah.
Thanks.
Yeah.
So let's just, at the risk of sounding too pedantic, tell us what philosophy is.
Wow.
Or let me be more precise.
Okay.
What is philosophy today compared with maybe 100 years ago, 200, 300 years ago, back to Aristotle and the famous sort of Greek philosophers?
Right. So I hope I won't be repeating the same stuff.
Who cares?
I only have 3 jokes, and I think I did 2 of them last time.
We got other jokes coming here. We're good. We're good.
Fresh. But that's maybe actually to the point. Some people have famously said that everything is just a footnote to Plato. It's all been done. All of the questions have been asked. But one of my favorite definitions of philosophy comes from philosopher of science Bas van Fraassen, who also
that's
was
a name. That's somebody.
Van Fraassen.
Let me tell you, Bas van Fraassen. It sounds like a Haagen-Dazs ice cream.
That's well, you know what yeah. They made that up. The umlauts on the right, like they're like, let us sound European to sell our pecan ice cream. Or whatever.
They're made in Jersey. Haagen-Dazs
But
is made
Fen
in Jersey.
Frosten is legit Dutch,
Gotcha.
which is like part of my heritage, right? But he says that philosophy, it might be asking similar questions, but every time you ask it, you're in a new context, new scientific context, new cultural context, new political context, and you're a different person asking it. And so there's a way that every time it's done anew.
And you could be a different person from yourself having asked the
Absolutely.
question even just a year or two earlier.
I think one thing, we tend to look really hard for coherent thought across a person's lifetime, but why should we expect that?
Well,
right?
we shouldn't.
We shouldn't, right? People change their minds, and people who think hard are the ones who change their minds the most, because I think there's a bit of humility there. So yeah, people, Aristotle defined metaphysics right after his book Physics, and for him they were similar things. They're asking about what kinds of things we encounter in the world, what their behaviors are, what the patterns are that we see. And that's still a decent way of talking about what science is. It's explaining natural phenomena, like physical phenomena, right? Understanding their relationships and their behavior and their patterns and all this stuff. So they started together. As the professions became a bit more specified, they started specialized. Yeah, thank you. That's the word. They teased apart a little bit, but even into the early 1900s, you have all these really famous philosophers like Ernst Mach and Einstein and Pierre Duhem and Poincaré and Lorentz, who
and
were
of Mach 1, Mach 2.
Speed of sound Mach.
Speed of sound in a medium, yeah.
Absolutely.
That same Mach.
That same Mach. They were philosopher physicists.
Go before them. Tell me, coming through Newton and Hooke, because they didn't call themselves physicists. They were natural philosophers.
Right.
So take me through that era before you land in the 1800s.
Yeah, so again, Newton is building on Descartes. And Descartes was sort of the worldview that was building on Galileo and Kepler and Copernicus, but doing so in a way that wouldn't piss off the Catholic Church. So it's kind of a weird thing. But he wrote his magnum opus, his great work, is called The Principles of Philosophy. And Newton is criticizing that particular book when he writes the principles, the mathematical principles of natural philosophy. Wait, did I get the title right? I only just called it the Principia, so I've forgotten by now.
Yeah. So what you're saying is Newton's famous work postdates Descartes' famous work, and is he poking fun at the title and making it more of a product?
He's trying to replace it. Right. This is what they build on it.
Yeah, so let me get the right title. So Principia Mathematica Naturalis. So in English, the mathematical principles of natural philosophy. That's the full title.
In Principles of Philosophy, there's 4 books. Descartes, right? There's 4 books. The first one is setting up his philosophical worldview, his epistemology, which is theory of knowledge. How do we know anything in the first place? And then his metaphysics, like what is there that exists for certain? And that is considered the first thing to do before book 2, which is his physics. So in order to even get to the physics, you have to talk about when do we know something.
Which book has the I think, therefore I am?
That is in the Meditations, which was published a few years before, in 41.
So he was already trying to go there.
So book 1 of the Principles is like a polished version of the Meditations.
All right.
And that's what starts his philosophical worldview is the first book, and then his physics and his celestial mechanics, and then onwards. The Principia begins with definitions, which arguably, Poincaré argues are not helpful, and there's a way that that's true. And then there's the general scholium, which means explanation. And the general scholium is where he gives his philosophical arguments for absolute space and absolute time. And it is after that philosophical framework is established that he derives the 3 laws of motion.
And gravity would come in there.
And gravity is even later down the line.
Right.
But the first thing that they considered having to do was talking about how we know what you know.
Exactly. Okay, so
and then do you know that you know what you know, and is it important to know whether you know if you know, or right?
I don't know.
I would say,
which is right.
Did he give the right answer to that?
For sure. Yeah.
Okay. So through that period, the various folks who are trying to do physics are fundamentally conjoined with philosophical foundations of why they're thinking that way at all.
Right.
Okay, so now, fast forward or slow forward into the 1700s, now take us to the 1800s.
Scientific revolution time, also actual revolution time for a variety of countries. Also,
America.
yeah, America,
and of course France.
Liberté, fraternité,
Liberté. That's right.
tobacco.
Oh, yes.
Wait, I don't know. Wait. I don't know how to say tobacco in French, which is probably a good thing.
Keep your stinking freedom fries. Okay.
Because we didn't like the idea of a monarchy. That's our history. Rebelling against a monarchy.
Yeah.
Anyway.
I see what you did there.
They're writing to each other and corresponding and setting up experiments. Boyle, Gassendi, Newton, Leibniz, the people who were still philosopher physicists in the 1700s and 1800s. They're also now working with Newton's Principia. And it's known pretty early on that the Principia doesn't answer everything. Like the law of gravity is action at a distance. Because it just says, imagine a universe with nothing in it. If two masses just popped into existence, they would somehow immediately feel the force between the two, right?
Okay.
And there's no time for the force of gravity to travel and say, hey, other planet, this is what you should feel toward me. No, it's instantaneous. So people knew there were issues. And one of the main people was Émilie du Châtelet, who wrote a book called The Foundations of Physics.
Ooh.
Right. So before, maybe...
When was that? I'm going to pick that up.
She's in the mid-1700s.
Thank you for that.
And she's experiencing a renaissance right now. For a long time, she was just known as Voltaire's lover and mistress, and she hosted many salons.
Salon.
This is how I feel about. I don't know how to say French things.
Okay. I want to just make sure the timeline is established here. Right. So Newton's greatest work was done in the 1600s,
1687.
spilling into
early
the early 1700s. Voltaire comes around mid 1700s.
A little earlier, yeah.
A little earlier,
I think.
And du
Châtelet is the same time.
Du Châtelet, and so they're coincident in time.
That's right.
Yes.
And she's hosting a lot of the intellectuals of the time, and they're having interesting conversation. But she's also in charge of teaching her kid, her son, physics, and she's disappointed with all the textbooks, and she does what many people do. She writes her own. And the first thing she does...
As one does. You did that with your kids,
you
too.
See all the textbooks my kids are reading. They're all wrong, because I wrote them.
Do you put as, the byline is Lord of Comedy, comma, your father. Yeah. Anyway, she... Before writing this book of Foundations, which again starts with a philosophical framework and goes from there. It starts with the principle of sufficient reason and the law of non-contradiction and the rule of sort of proper reasoning.
Wait, law of, do they declaring that it's a law?
It's an axiom.
Okay.
Yeah, you have to start somewhere. So
you lay down some rules.
That's right.
Rules and regulations.
Yeah,
and
you got to bite the bullet somewhere.
And what follows derives within those constraints.
Yes.
Okay, gotcha.
So, but she's also the one who translated the Principia into French. And I guess current French physicists still read her translation, but she didn't just translate the Latin into French. She filled in gaps. She wrote a thick commentary.
Wow.
And so it's her physics that has trained.
You pull out Newton, say, Newton, you need help.
Here's what you left out, Newton.
Exactly. And so it was, people kind of got it. He's not telling us everything. He's given us some parameters, but there's more work to be done if we want to really know why things work the way they do. So,
and how many lady physicists existed at the time?
Hard to know because, again, this physics philosophy split isn't totally there. So while there were just a few women, maybe, who were doing experiments of any kind, I'm not sure I know any. There are a lot of women doing philosophy.
Wow.
Corresponding with Leibniz, corresponding with Hume, interacting, writing, influencing Leibniz's thought.
Interesting, because I have a book which is Leibniz's letters.
Yeah.
And there's all manner of people that are on the other side of those letters. I'll take another look at them.
Yeah.
Why we all know Leibniz today. Just tell Chuck.
Newton both developed calculus more or less at the same time, which I'm sure you woke up this morning saying, you know what? I'm dying to know who invented the calculus at the same time as Newton. But anyway, he thought that space was not a substance. It wasn't a thing. It was just the relationships between stuff.
Okay.
A relational view. And so he objected to the idea Newtonian absolute space and absolute time, which is not really a stuff either, but it exists independent of matter. So it's like a thing in Newton's ontology. Like when he's listing the stuff that exists, space is there.
Space is part of it.
But for Leibniz, it just is how we understand the difference between the distance between matter.
I'm confused here. There are two independent calculus, and they both work. That sounds weird.
No, you know they're different because all the notation is different.
Yeah.
And in physics, we retain a lot of Newton's notations.
Okay.
But in pure math, it's all Leibniz's. You know, the integral signs and all these squiggly
Right.
That's Leibniz,
symbols.
right?
That's Leibniz,
Yeah.
It's all Leibniz.
Okay.
And so Leibniz is a little more elegant than Newton's. Newton was like, let's get in and get the job done and get out kind of thing.
All right.
But I'm impressed that it would happen at this basically the same time and independently.
I love calculus. I don't know why people give it such a bad
Well,
rap.
I didn't. That's the thing I never thought I'd hear this morning.
I love
When I woke up this morning, that's what I thought I'd never hear.
Is that a bumper sticker on your car?
I love
I don't have a
calculus.
car,
Oh,
but if I did, that would be one of them for sure.
All right. Nope, that's lame. Ready? Do you harbor questions about the universe? Some long-held bit of cosmic curiosity lingering within you? Or questions about anything at all? You can become a Patreon supporter of StarTalk. You have access to our exclusive question line on our website. Those are where we draw our questions for our cosmic queries.
Some of the most extreme objects in the universe.
StarTalk is a work in progress where we, every month, come up with some new way, some new idea, some new understanding of how to bring the universe down to Earth. We could not do that without your support. Thank you. And as always, keep looking up. So now we got them. Now take us now into the 19th century.
As technology gets better, we're able
The Industrial Revolution.
Yes, and all these, like we start moving from talking about forces and inertia and stuff we can't fully analyze, and we start getting quantitative about conservation of energy and about like tweaking frog legs so we can understand how muscles work, and psychology is coming into its own, and sociology is coming. Like the different fields start to distinguish themselves, and at the same time, like universities are being built and growing, and the different faculty at universities are getting set up. Professional societies like the Royal Society and the Paris Society of Scientists are growing. So now you have communities growing up where people share their findings, and it's international, at least in the West, and so on. It's a long and interesting story, which other people could probably give a better version of, but it's this increasing ability to quantize and specialize. The more we learn, the more there is to sort of, I was thinking the other day, wouldn't it be great if we lived at the time of the Library of Alexandria? Because like you could really have said, I've read all the books in the world.
Yeah,
Wow, look at that.
This is not possible
I think,
anymore.
Elise, I think that was true up until much later than that.
Really?
Like rumor has it, I'm heard told, that up through the 1500s, highly educated people could have claimed to have read everything that was ever written.
Yeah.
Well, that's because it was all handwritten.
Real slow.
Yeah, but some people like Aquinas, they had scribes. They had like a room full of monks writing for them.
Just writing all day
And
long.
sheets.
Yeah. As they go into these communities, when does all of this lead to what we are? Because none of this stuff is cross-pollinating today.
Well, I wouldn't say none of it is. I would say it's harder to do.
Okay.
And I'd say people are still asking these questions. But we've built, and we touched on this last time, we've built up our universities in a way that we actively discourage people from staying as general as possible.
Okay.
Liberal arts training is being kicked like a poor little puppy, and it's like such an important thing.
Right.
And then when you get to graduate school, it's all over. It used to be like you would try to say general, even through your master's degree. You would take a little bit of, like you would learn everything.
Are you saying it's important because it just kept you loose?
Yeah. It kept you learning a bunch of other stuff.
Just
and
that kept
appreciating
the dimensions of life and of society.
Right. So, I mean, I'm going to jump all the way to the Cold War era. And if people are interested, like there is good history on this. And one book in particular is The Physicists by Daniel Kevlas. It might be a little outdated by now, but it just talks about the history of physics in the US and how it became so many different specializations and so on. But it was only after the Manhattan Project and after World War II that physics was properly considered a thing you could have as a career. It wasn't just something you learned as a young man at the university or one of the few women, but it was something you could you could bring home the bacon, right? If you actually did physics or engineering.
But at that point, physics is making bombs.
That's right.
They're important for national security, and no one is talking about philosophy at that point.
So that's when the transition kind of happens. It becomes, in the US, very pragmatic. It's about the shut up and calculate mentality. And that really dominates through the Cold War era because there's it's competition. But interestingly, in the 50s and 60s, James Conant, who was the president of Harvard and a physicist and a chemist.
I didn't remember that about
Conant fought really hard for even his physics students to know the history and philosophy. He understood it as so important that he built it into Harvard's program that even if you were just studying physics, it wouldn't be like writing down lab notes and doing calculations. You would also take a history and philosophy of science course.
You're saying explicitly and implicitly that coming out of the 19th century into the 20th, especially post-war, the field of physics has borders in a way where other ways of thinking can't get in.
Yeah.
And you're saying that's to the detriment of physics, not to the detriment of other fields? How would you characterize that?
I think it's to the detriment of any field, not just science, when those walls become impermeable.
I think walls are a very good thing.
Stop. Physics, as far as I can tell today, still suffers from this border problem.
It makes sense because we get hyper specialized because we know so much and building on so much. We're asking just that many more questions, and we have that much more technology to explore. So, I mean, the blossoming of many flowers is a good thing.
So, how do we use you?
Well, maybe I don't want to be used.
Okay, sorry.
Maybe I get to exist in my own right because it's a beautiful and wonderful human endeavor.
It came out wrong.
No, I know what you mean.
How do you help us?
Okay, we help each other when we share ideas, when we have conversations like we're doing now. So, for instance, I was just talking about Mach. He was an important influence on Einstein. When Einstein wrote an obituary that everybody read for Mach, he said, one of the reasons I hold this person in such high esteem as a physicist is because he kept asking about what is the proper goal of science. And that guided how he did science. But what is the proper goal of science is like a guiding principle. It is itself a philosophical principle, the same as we might say at a more intimate level in physics, like that choosing something that's parsimonious or beautiful or simple or whatever. There's no reason why the earth should or why nature should give a damn about those principles.
About our aesthetics.
Yeah.
Right.
In fact, that nature is uniform at all is something you have to assume to even think science is worth doing in the first place. So like there are moments you have to sort of buy into certain untestable principles to consider science worth doing. But the thing is, these are important things, but the concepts that we use too. So here's a good point. Space and time, the way that they're used in Newton, absolute space and absolute time, and whether or not they're important for his derivation of the three laws and his law of gravity and all this, was an important question to ask. But Mach and Einstein and others at the end of the 19th century are clear that electrodynamics isn't going to work in absolute space and time. Like they knew things didn't fit together in the right way. And so they knew that one way to attack this, to get to new physics, was not just going to be to push around the equations, but to reevaluate the basic concepts.
And just to be fair to Newton, the whole electrodynamics, the physics that came to be understood that we call electrodynamics was not yet there for Newton.
Yeah.
Right? So he's working in his own, like you said, you work in your own world, you come up with what works. Later on, we keep going.
Yeah.
Right.
So, late 19th century, there's tension between these different, like really these pillars of physics, like thermodynamics, statistical mechanics, and I'm blanking, sorry, Newtonian mechanics, sorry. Classical mechanics. And it's Einstein. Einstein says that it is not the physics in him, as it were, that allowed him to get to special relativity. It was that he said, what do we mean by this term simultaneous? And what do we mean when we're talking about space and time in different frames
These
of
are
reference?
not questions physicists typically ask.
Well, they were back then. They were for the heroes of Einstein, and the class of people who were philosopher physicists was a significant class of people
At the time.
a century ago.
Yeah.
That's right. So that it wasn't for the last 50, 70 some years is partly because of, like, there are political reasons for it, like the intellectuals who came to the US from Germany during the wars, the way that they entered into the academy and began to teach physics and philosophy and think about this stuff. There are whole classes at the graduate level you could teach just about why the Vienna Circle, a particular philosophical school, which was all scientists, influenced the way American philosophy and physics relate to one another. So it's a complex and interesting story. But the end point is that if we take Einstein's word for it, this going back and saying, are we really understanding this concept the way we should be? And this is what we're doing right now with gravity and trying to understand the quantities of gravity, and what we're doing right now with causality. Like, is there a quantum notion of causality, or what does causality mean if space and time are even crazier than in a relativistic framework? So it's the reevaluation of these basic concepts. And that is a philosophically motivated question, and asking, how do we know? We talked about this a bit last time. We're getting into regimes in physics where we're beyond what is empirically testable, at least for the foreseeable future. What then do you use? What are your criteria for judging what is better or what is worth pursuing? Who do we fund? Where do we send our best graduate students? That is based on who has the framework that you find the most compelling, whose view about the nature of space and time, how general relativity and quantum mechanics fit together.
So Brian Greene's best-selling book, The Elegant Universe, just in all fairness to him, that was not his original title.
What was it?
It was some more boring title. The publisher chose that, and that had a certain cachet with the public.
Yeah, well.
But it implies that we as scientists are in search of beauty, majesty and elegance in the universe, as though it's waiting for us to discover it.
It's like the universe is going to a cocktail party, darling.
Presumably that's still okay to have some prior expectation for the universe to guide your next questions.
Well, you shouldn't do, like, it's important and unavoidable as a guide, right? And we sort of talked about this framework, this worldview thing, like, it's going to be there, but elevating those guidelines to the level of dogma is when we get in trouble.
Okay.
Or just
because then it affects who you hire into departments. And
but it also affects what you consider the correct route to go.
It shapes your whole outlook on how you're going to approach everything.
Right.
You know, because you're like, well, can't do that because we've already made up in our mind that this is the way it's got to go.
Right. Or I mean, you have to bet on a pony, right? I mean, if you're choosing whether you're going to pursue like canonical approaches to quantum gravity, like loop quantum gravity versus covariant, or like gauge theoretic, like string theory, like what Brian Greene does.
What is he saying, please?
I'm pretending I'm following.
I don't have any idea what you are talking about right now.
Different approaches to solving a problem that we know exists.
There are like two basic. This is a very crass way to put it. Forgive me, but there are two big approaches to how to unite general relativity and quantum theory.
Okay, that's
and
so
one
far
of the approaches is trying to build a theory of everything from the ground up. String theory is kind of like that.
Heard that. Go ahead.
Okay. The canonical approaches say we think quantum theory is the most fundamental theory, so we're going to try and bring GR into that framework.
Gotcha.
But that is something we can never empirically prove which is the right path to pursue.
Look, I said why I'm leaning that way.
Yeah.
Because no one has ever found a quantum physics prediction that was false. It is so correct that, oh my gosh, all right. But now you go to general relativity. It has known limits. It can't calculate the center of a black hole. It can't calculate the moment of the Big Bang.
Yeah.
It fails.
If you can't calculate, stuff about black holes, get out.
Get
out of physics.
No. What I'm saying is,
people. I'm not talking about people. I'm talking about abstract entities.
Right. What I'm saying is, if you already if you already know the limits of general relativity,
right,
and you don't know the limits of quantum physics because you've never seen the limit.
So you're
I'm thinking quantum is more badass.
That probably goes in here, not the other way around.
Or of course, there could be a third entity
There could be a whole
that
other
absorbs them both.
Yeah. So, and then there are some alternates to these approaches, and they're considered a little bit fringe, but that means like it's hard to get good grad students to come and build your, and like there are sociological factors too. But yeah, back to this notion of guiding principles, some of them have been like huge issues in the history of science. And I talked about space and time, but one of them is like objectivity, right? This idea that you ask the person on the street, what are the adjectives that describe science? And they're like, well, it has like a corner on truth, maybe. That science has like this corner on capital T truth. And there are some philosophers and scientists who continue to say things like this, but that's wildly problematic because that itself is a philosophical view. Like, how would you know, as one single person even, that this is a special kind of truth? Now, it's true that we have
How true is
empirical medium capital T, like the slash is somewhere between quasi truth.
Different size T's to begin the word truth.
I'm going to say like 50-50. I don't know,
All
like
right.
20 proof. Well, that's weak. That is weak sauce. Anyway. Objectivity is also one of the things that's supposed to make the knowledge and the truth that comes out of science a bit more untouchable. But objectivity is where the development of quantum mechanics gets you in trouble. Because if you mean objectivity to be something like, when we do science, we can rope off this realm or this system, and we can poke it and prod it and study it and ask lots of questions, blow it with hot air, like see what comes out. And that's how you do like you have to assume that there's some divide between your apparatuses that are measuring the thing and the thing itself. This is a very old problem. I think it's even Aristotle.
It's a measurement problem.
It is. And it's an old one, except in the sense that like Aristotle, I think, or somebody said, like, if you want to study a bird, you can watch it flying around in its habitat and singing and all that, but you also like need to dissect it and look at it, but you can't have them both really, because if you've dissected the bird,
he can't fly around anymore.
I thought that was
you
Feynman.
don't want that happening, right?
Yeah, I thought that was Feynman had a whole lecture on birds.
Oh, then I really don't want to quote Feynman for a lot of reasons.
But I like what you said, where if you really want to know what a bird is, you have to open it up, cut it open, and then it's not the bird that you were studying.
Right.
You just influenced the thing you were trying to understand.
Right. So we know how to sort of quotient out that engagement in classical theories to a point that we can get very nice predictions of like football trajectories and
hence the idea of an objective truth.
Right. But what happens in quantum mechanics is, and Bohr and many others were realizing this already 100 years ago, right in 1925 when it was first developed, that there's
100 years ago, we're in the centennial.
That's right. It is the 100th anniversary of like,
we did a whole live show at Beacon Theater celebrating the centennial.
There's been a lot of celebrations. It's the International Year of Quantum.
Yes.
I'm just going to have to sleep for all of 2026. But that's when wave mechanics was developed and new physics.
Yeah,
anyway.
every year. And Hubble discovers that we're not the only galaxy.
Wow.
1826.
There's always something to celebrate, right?
1926, right. Mm-hmm.
There's a way when you're talking about quantum systems, like photons and electrons and these things, that you cannot avoid interacting with a system in a way that cannot be quotiented out. Okay. And so this is something that Einstein continued to look for. In particular, he thought that when a physical theory is complete, that means that you can give a mathematical state bijectively. That means there's a mathematical state that corresponds to some real system in the world.
Did you just use the word bijectively?
Yeah, sorry about it.
That's a word?
It just means in both directions, like that you can read from the math to the world or from the world to the math.
Interesting.
That's all.
Love it.
That there's a nice correspondence.
Bijectively. Cool.
And I think somewhere else Schrödinger says, yeah, Einstein, he likes a map with a little flag on it saying, here's this system and here's the system, right? And because in Schrödinger's wave mechanics, you can't do that anymore. Because once two subsystems have interacted quantum mechanically, and we pull them apart, and even after interaction has ceased, Einstein says, you should, if you have a complete theory, you should be able to give a description mathematically of this guy over here that doesn't make reference to this guy over here.
Oh.
They're totally separable.
That's kind of an issue, right?
It is. It is.
That's a little bit of
because
an issue.
entanglement
Right.
can be understood as non-separability.
Right.
In fact, it means after there's a quantum interaction and it's a new kind of thing that it's not mechanical, it's not thermal. Like you don't even have to like.
It's a new thing.
It's a new thing, and it's not just a new thing. It is, according to Schrödinger, the thing that causes a departure between classical theories and quantum theories. When systems interact, something weirdly different happens, and you can no longer talk about the system, the physics of one,
without considering the other or referencing.
That's right.
Because wow, that's wild.
It is wild.
I love it.
Okay, but in all fairness to the objective truth people, they're really. I don't think they ever intended to include quantum systems in it. You're talking about the macroscopic classical physical world, right?
Well, but
can you have both? I mean, can you just isolate the one for those circumstances and then have the question of the other, like philosophically and I'll say physically? Is that possible?
It is, but even Einstein realized right away that quantum theory, if it's about the really small stuff, what is the big stuff made of?
Well, yes.
A bunch of the really small stuff.
Right.
So there's a way that Schrödinger's mathematical description of the quantum stuff that means you can't separate out systems, that's part of it, should also apply at the macroscopic scale. So there becomes this whole issue of how do we explain, first of all, what this theory of small stuff is doing, and then what happens when we get to this level, because at this level, it doesn't look like you and I are entangled or anything like that, right? And we can give really good physics explanations now for why that's the case. But a lot of people like mistakenly think that the Copenhagen interpretation, like Bohr and the others, that were so intent on recovering objectivity so we could talk about quantum science, made a sharp and fast distinction between the classical world and the quantum world. Like you have your measuring apparatus, and that is a classically sized thing so that we as humans...
It's a blunt instrument.
It's a blunt instrument. Yeah. That's right. And then you have the quantum system that it's interacting with. But in order for them to interact, we have to talk about them in the same theory.
However, aren't you allowed to say macroscopic objects, all these wave equations average out and to get to this classical result?
But we know better than, it's not just averaging out, it's a process called quantum decoherence. Which is
sure.
What is
entanglement,
that, please?
Yeah, entanglement itself. It's the same problem about objectivity. But first of all, I just want to clearly, like Bohr never, in his post-World War II popular lectures and stuff, he sometimes talks about a classical world. But he never, ever, there's no evidence that he believed there was some really separate realm. Like it's a continuous situation. Thank you, Chuck. You're my friend. You're here for me. It's a continuous situation. And he's like, okay, it's continuous, but we are physicists and we go into the lab and we look at a machine with a pointer. We have to be able to talk about that. So there's this pragmatic aspect of what he's saying. This pragmatic objectivity. It is the failure of our being able to give this hard and fast divide between the object we're studying and the world around it that accounts for why we can't see things as quantum mechanical. It's because the quantum systems we're looking at are in fact interacting with lots of other stuff.
Einstein said God doesn't play dice with the universe, famously. Are philosophers landing in a place where there is objectivity in quantum physics?
It depends.
Sorry, are they headed to a place? Is that a goal at all?
Well, if you mean objectivity as intersubjective agreement, like that we could go into each other's labs and agree on the results of what each other see, then clearly, yes, that's a part of what we want.
Okay, of course, because otherwise there's no science without that. Okay.
But I mean, I was at the 100th anniversary of quantum, like Helgoland conference. Helgoland is the little island in the North Sea where Heisenberg went to do a wee bit of cocaine and to finish how to do...
Where do you get all the scoop on people?
And I'm going to tell you
I read their letters.
Oh, the letter? Because it's not in their books.
Yeah.
Right.
Let me just say this one thing, make a correction there. There is no such thing as a wee bit of cocaine.
You can't do a quantum. So they got a bunch of physicists together. They had a panel session with a number, 4 recent Nobel laureates in physics.
Cool.
And they're talking about the Bell experiments, which test entanglement. and show that they're not communicating faster than the speed of light or anything like that. And it's something we call non-locality, which I would characterize as like the signature that we can measure, the signature of entanglement. That's a poetic way of putting it. These physicists won the Nobel Prize for designing experiments to test this, and they could not agree on stage what non-locality meant about the world.
Okay, so tell us what non-locality means.
I'm not going to be able to supply an answer if two bell no Lord. I think it's just indicating that systems are quantum interaction is a kind of interaction we have never studied before in physics.
So non-locality means these two particles that are entangled cannot be described independently.
That's right.
Of each other. So this is not local. It is connected.
So it's not just that, because we could do that classically, right? If Chuck always wore different color socks, and I saw just one of his socks on a given morning, it's like he's wearing a brown sock, I could know something without measuring his other sock. I would know that it would be non-brown.
Exactly.
Right? Okay. Right. That's purely classical, not interesting. What makes it very non-classical is the idea that once these systems have, for all purposes we believe, stopped interacting, they're not communicating, there's no information going between them, nothing is exchanged. While they're in flight, we can at our measuring device for this guy, set it to measure some quantity or other, spin with respect to some angle or something.
Measuring a quantum property of that entity. Yes.
Yeah, some property of that entity. And the other one will know
what it is that was measured and what state the other thing is.
So therefore, it's not local.
So, right.
That is the non-locality. So it's not just that there's a correlation between the two. We have lots of classical correlations that we love. But it's that these correlations cannot be explained. The correlations exceed like just statistical randomness.
Can you one day?
Yet they can't be talking to each other.
Can you one day?
There you go.
They can't be communicating unless you want to ditch the speed of light. And most people are happy to say, like Chuck woke up this morning and said, I'm happy with the speed of light being what it is.
Wait, Elise, why not go full Monty here and say the two particles are connected via wormhole?
So we could give alternate explanations, but wormholes they would have other effects, wouldn't they would have
who
other...
knows? It's an entanglement wormhole. I mean, who knows? With a wormhole, you're not moving faster than the speed of light. You're just cutting through the space-time continuum instantaneously.
I think it would be hard because entanglement, non-locality is so ubiquitous. I think it would be... It's not impossible, of course, and this is where your guiding principles come in, but to just think that wormholes occur whenever but also entanglement can happen with respect to different properties of a thing, and it can change over time, and it can be multiple systems depending on those. So it is a really complicated relationship.
Okay, so now I measure one of the particles, the other one manifests itself with the complementary properties, and now I've just they're no longer coherent.
They're no longer entangled after you've done that measurement.
Okay, so now they're local particles.
Yeah, and in fact, the measurement that you do, the physics that we're doing is all local over there, right? But yet there's this thing we can't explain.
All right, so my question to you is it the physicist who's taken a little bit of philosophy that'll help them address all of these questions? Or is it the philosopher who's taken a little bit of physics who might get us out of these conundrums?
I think we could use all the help we can get. Let's all talk to one another.
Who cares where it comes from? All hands on deck.
All hands on deck.
I mean,
I'm sorry, because I'm still, you guys were moving very quick, and I'm the guy sitting here without any PhD of anything. Okay,
you don't have a PhD?
Yeah.
Somebody give this man an honorary doctorate.
I know, yeah. Who invited you? Okay.
So, based on what you just said, because I'm running it back in my head, is it the actual measurement at the time of measurement that makes the entanglement? Or is there ever a decoupling at all? Or are they measured and then tangled and then forever entangled?
All of those things can be true. We've developed ways to do weak measurements, which sort of lightly tap the system. It's like in a way so you can gather some information, but not fully decouple it. But and again, the degree matters. Like there are some limits on how entangled certain numbers of states can be with respect to some, like,
Very
so
good.
this is why we can use entanglement as a resource, and it's like to help us explore different like topologies in holography, which is, ADS, like anti de Sitter space, and how it relates to conformal field theories, which I don't really know about, and I want to figure out, like, I gotta but they're using entanglement as a way to probe unmeasurable stuff.
Okay, so we got to land this plane. So
Okay.
the way I want to land the plane is to get you,
That is super cool, man. I'm telling
It's
you.
very cool.
I mean,
It's
unbelievable.
Yeah.
get you to tell me what the future of this creative thinking will bring to quantum physics. Is the goal state to turn quantum physics into something as intuitive as classical physics, where with a pathways of understanding? That's obvious that it should do that. This particle pops in and out of existence, of course. Or will it just remain statistically mysterious and, like Einstein said, God does not play dice with units, but maybe God does. My answer's gone. Maybe God is a gambler and just deal with it.
Yeah. People have different questions about that. So here's another, like, if you're a physicist who does quantum theory, or you're an experimental quantum physicist, and you believe that the universe is not statistical, then you're going to design tests that try to get beyond that. But if you think the world is ultimately indeterministic, then at some point you're going to move on. Yeah. But I've already said, I think this is just my guessing, again, from conversations I have with practicing physicists, but thinking about quantum mechanics is never going to be intuitive the way classical mechanics is, because we as evolved creatures, the way we are, started doing science in terms of position and like with things we could see and measure, and apples and arrows. And
we didn't evolve in a quantum state.
No,
right.
In fact, you could very easily argue that knowing quantum theory is evolutionarily maladaptive, because it's a bunch of nerds like myself sitting around doing problem sets, and here comes the saber-toothed tiger. So it's good for us as a
you would be
species.
summarily removed from the gene pool.
Yeah,
Yes.
I think so.
I prefer
Like,
a classical.
it's a good thing for physicists.
A classical understanding of the saber-toothed tiger
So we
wins
built-
every time. Yes. Okay.
If that's the only thing that the audience takes away, that's a good one. For those who live near saber-toothed tigers. They're extinct, right?
Yeah. Yeah.
Biology is not my area of expertise. Okay,
But
I got news for you. The regular tigers, they'll
enough.
make a
Eat you too.
difference.
We'll stick with the regular
they're
tigers.
good enough.
we got sharks and things. It's all good.
They'll eat you too. Plus, they're on the list for becoming de-extincted. The saber-toothed
the
tiger.
fact that we can do that now. Phew, so cool. So there's a way that quantum is never going to be intuitive to us the way it is. But that's why engaging with these philosophical questions, we're going back and asking, what are we doing when we do this test? When we do tests, are there loopholes in the logic of how we're doing this? Are there things we can be testing we haven't thought of yet? Are we using the word causality or space or time or background? Like, are we using these in a consistent way when we set up our experiments? Are we testing our assumptions? Like, these conversations as well, we're so wedded to the classical picture of things that understanding
And it's not our fault. We evolved that way.
Very natural, right? But it also means that we have to do a lot of work to continue unmooring ourselves from that
Ooh,
perspective.
I like that
I
phrase.
love it.
Unmooring.
Yeah.
So, okay, all hands on deck.
Keep doing it.
No, it makes sense.
Yeah.
I mean, it's like really, it's kind of a, an ossification that happens,
That's another really good word.
because of the
Ossification?
practice itself.
Yeah.
And then what you have to do now is, in order that we can become more elastic, this is where the philosophy comes in to help change the thinking altogether so that we can go in a different direction.
Right. And in the ideal world, there would be more cross-pollination, but also the way we train physicists would be, because there's lots of philosophy that doesn't really talk about physics or take physics as its input the way philosophy of physics does. Ethics, epistemology, social political philosophy. These are important areas of philosophy that leave physics.
Ethical philosophy, religious philosophy, even economic philosophy.
Philosophy of law. Philosophy of the emotions. Like these things can stay pretty far.
Space law. That's another frontier where they need some philosophers.
Every time I meet a lawyer, I ask if they're a maritime lawyer because they're going to be the first ones who develop. They're going to be the ones. A good friend.
Has your satellite crashed into another satellite?
That's not the guy.
No, listen.
We can get you what you deserve.
That's not what we're talking about by space law.
Actually, it's not far away. I mean, there's a nearest trajectory between Earth and the Moon. Who's going to police? Is there going to be toll booths along that? Like, who's going to police? My brother is co-founder of Carmen Plus, which is an asteroid mining startup, and they have a lawyer.
As everyone's brother would be. Yes,
of course.
We all have.
And
that.
what they do is super cool. But they have to think about these questions like, do we tax stuff that you mine from asteroids? Who owns this stuff? These are really important questions. So yes, but that physics training in the US would involve some pausing and stepping back and looking at the history of the field and asking philosophical questions.
Is there a country that's doing that now? And we're lagging behind them.
I think there are. I don't know at the university level, but this was what was really exciting at Helgoland is I met a lot of young, like early career folks in physics at these great labs all over Europe, in China and in South America and some in the US. Although, to be honest, most of the labs in Europe are hoping to get some of our best scientists who are leaving. This is a real
Phone
thing.
calls have been made, yes.
We're losing some of our top scholars.
I wonder what's going on with that.
But the young generation wants to study this. They are interested in knowing these things because they understand how wedded it is to the edge of physics that they're asking. So I think if enough people ask for it, like vote with your dollar, right? Ask to be taught these questions when you're learning physics, and it will.
A reminder that when you're young, you're a little more irreverent in your thoughts anyway.
Yeah. You're a little bit less, like you haven't built a whole career in a particular groove, so you can sort of hop over.
All right.
Yeah.
Well, Elise, thanks for coming back.
Fascinating.
Thanks for inviting me. I have a a good time conversing with you guys.
Okay, and you're just up the street. I mean,
That's true.
Right up there. City College is up in 138th Street, right up there in Manhattan, a few miles north of here.
Can I ask one last question, Neil?
I guess so, sure.
I know you've said, this is personal, and so it doesn't have to go on the air if you don't want, but I know you've said a number of things about philosophy of science and philosophy in general in the past. But you seem really genuinely curious about these things. What's that about?
I would say my comments on philosophy have been caricatured.
Oh, okay.
And so I can be very explicit.
Fair.
Okay. I have yet to see someone who has earned a PhD in a philosophy department in the 20th century contribute materially to our understanding of the physical sciences.
Oh, it's been done already. Yeah.
I just haven't.
But also, I mean.
So who is saying that? Is the philosopher saying that, or is the physicist saying that?
The physicists have said that.
Okay, so
there are contributions.
What's the single best example? Single best.
Adam's got one.
You're here.
No. I'm calling on my Ask a Friend.
Okay, ask a
phone friend.
I get a phone a friend.
Phone a friend.
So Abner Shimoni was a physicist at Boston.
Was a physicist. So he's formally trained as a philosopher.
Abner Shimoni has formal training in physics and in philosophy.
But his PhD is in what?
Both.
What?
Well, there you go.
He has 2 PhDs.
But that's less the point. The point is when you read these papers, the reasoning is philosophical, logical reasoning.
Just don't get me wrong.
Okay.
I'm not saying that physics can't be helped by philosophical thinking. I don't know any good physicist who isn't thinking on some level philosophically about what they do.
Great.
And in the field of astrophysics as well.
Good.
There's always a philosophical dimension.
Sure.
So the precision of my comment about philosophy has just been, what is the value to the physical scientist of someone who's spent their entire career, academic training in philosophy?
So
and I compare modern times to how frequent those contributions came a century ago. And so if this is one guy, maybe there's more examples, but I'm just contrasting the utility relative to what role philosophers played back in the day.
Yeah, so I said this last time, and it's worth repeating. Saying that something is only important in as much as it contributes to science is a really dangerous point of view.
Yeah.
That said, it still contributed to science, but it is worth doing in its own right. But it is worth doing philosophy of science in its own right.
I'm not denying that either.
And I don't think it's also very always quantitative. I don't think there's a hard and fast line between these disciplines, which is why they were for thousands of years the same pursuit, and why in some arenas we're seeing them coming back.
But I never said it wasn't worth pursuing.
You've just been Shimoni'd.
No, I never said it was. I didn't say it wasn't useful as it's in its own field. I'm just talking about how useful it used to be to physics to have a philosopher in the room.
Right.
And
I think
that utility is now absorbed by physicists who are thinking philosophically, rather than a person whose entire training is in the philosophical world. And so I just
have these physicists themselves been trained in philosophy?
They might have, but not as
not very much. Have they taken philosophy classes?
Probably, yes.
I actually maybe an intro philosophy class as undergrads, but I'm willing to bet most of them have not taken a philosophy of science course.
Probably most, but some have, sure.
So there's a difference between like stepping back and thinking, which everybody should do if they're good practitioners of their, but there's just different ways of viewing the world that, again, I do have training in science, and good philosophers of science will have some engagement with the science itself and the people who are practicing it now. And when we have conversation, it's interesting. It's interesting, and we learn things. It is a dialectic. So it may be impossible for those fields to merge again, and maybe that's not the end game. But to have a conversation is very fruitful, because I change the way I think about how physics is being done right now. I learn about what they consider the interesting questions, how much progress we've made. It is all very interesting.
So why isn't this? So then we should promote more of that. I've been like 4 or 5 different academic institutions, and at no time is the philosophy department having lunch with the chemist, the physicist,
and
or the biologist.
therein lies the problem.
Yeah.
That's what she's saying. That's the problem.
Yeah.
You know?
And then when we do talk to each other, I think, yes, you're going to find people who are like, well, they don't have anything to do with each other. And you're going to find philosophers of science who are saying a bunch of stuff that has no connection to real science at all. And it could still be interesting. But if you're doing philosophy of physics in a way where you're trying to engage, you have to actually engage.
Maybe what I'm observing is the empirical fact that this doesn't happen.
Yeah.
The philosophy departments don't have lunch with the physicists.
We should.
And so I'm observing that reality and commenting on it.
Yeah.
So that's all it is.
Yeah, that's fair.
Because I long for the day.
Now that you have observed it, that reality is now entangled forever. So now it has to happen.
Actually, that's the observing that would destroy the entanglement.
Oh, that's right. They can't do it anymore.
So
sorry.
This is the comedic inversion of that. At least let me get you, take us out with Einstein's comment on philosophy. Do you remember it? Okay. He probably had several.
He made many.
Like I got my,
Which one are you hoping
one.
for? The history and philosophy?
No, it's not that deep. This is very off the cuff of him. Sometimes when I think about philosophy, I feel like I'm chewing on something that's not in my mouth.
Where's my book? Hand me my book.
Oh, okay.
I want to read the quote.
Okay.
One quote from Einstein that's a legit quote.
Thanks for reminding me that the Einstein Paradox, this is an academic...
It's an academic text.
Academic text.
It does presume some acquaintance with quantum physics, but just, a scooch of quantum.
Wow.
The Einstein Paradox, the debate of non-locality and incompleteness in 1935.
The originators
this is very,
of the theory...
thesis. That's like a title of a thesis right there.
This is intricate work.
Yeah.
It is intense work. So this is Einstein writing in June to Schrödinger. I'm trying to figure out what on earth quantum mechanics means. Dear Schrödinger, I was very pleased about your detailed letter dealing with our little paper. The actual difficulty lies in the fact that physics is a kind of metaphysics. Physics describes reality, he puts the scare quotes in, but we do not know what reality is. We know it only through our physical description. They are wedded together.
Wow.
Inseparable.
That's pretty cool.
He called him Schrödinger, not Erwin?
Didn't I say dear Irwin?
No, you said dear
Oh,
Schrödinger.
dear Schrödinger. No. Just like buddies. Like if you're playing a sport, you don't say, hello there, Terrence. I have, in fact, played sports in my life, despite what that sounded like.
Okay, there it is. We got to wrap this. Well, thanks for this second visit.
Yeah, that was
anytime.
To my office here at the Hayden Planetarium.
It's great stuff.
It's good to be back with you guys.
Yeah, this has been another installment of StarTalk. Let's call it the Physics of Philosophy edition. Ooh. Chuck,
Always a pleasure.
you are Lord of Comedy.
Yes, kneel before me.
Until next time, I'm Neil deGrasse Tyson. Keep looking up.